Hello and welcome to the series of instructional videos for the third year Analytical Chem Labs. I'm Dr. Robin Studley, and this video will be about the instrumental setup for atomic absorption spectrophotometry. The instrument we are looking at is the Agilent 55B atomic absorption spectrophotometer. What we see today will be very typical of a double beam atomic absorption system. This is a top view of the instrument with the cover off. Let's take a look at the path light takes as it travels through the instrument. Light from a hollow cathode lamp is split by a patterned mirror into a reference beam and a sample beam. The sample beam passes through the burner compartment while the reference beam bypasses it. A rotating chopper alternately passes the reference and sample beams towards the monochromator. The monochromator separates the light's different wavelengths. Light intensity is measured by the photomultiplier tube, which converts the light into an electrical signal. Now let's look at each step more closely. The light source in this instrument is a hollow cathode lamp, or HCl, which is a source of highly monochromatic light. Each lamp is specific to a certain metal, so if you analyze more than one metal, different HCls are required. When a voltage is applied to the HCl, the inert gas inside is ionized. These ions are accelerated into the metal cathode, sputtering atoms of metal from the cathode. The sputtered atoms collide with atoms of the inert gas, leading to excitation. The excited metal atoms emit photons as they return to the ground electronic state. The photons pass through a quartz window and are reflected by a mirror before arriving at the patterned mirror. The patterned mirror separates the light from the hollow cathode lamp into two beams, the reference and sample beams. The sample is introduced into the instrument through a capillary and is drawn in towards the nebulizer. In the nebulizer, the sample is mixed with a fast-moving flow of air and fuel to create an aerosol. Baffles in the nebulizer, which are also called flow spoilers, help to ensure complete mixing and remove the largest droplets of sample. Let's look at the flame and the sample beam. In the burner compartment, the flame itself acts as the cuvette. Sample in the flame absorbs some of the light from the sample beam. The color of the flame and the wavelength of light it absorbs depends on the analyte introduced to it. Here we're alternating between aspirating samples of water and strontium into the flame. The flame has three different regions: the primary combustion zone, the interzonal region, and the secondary combustion zone. The height of the beam above the burner, for best sensitivity and precision, varies with the analyte. After the burner compartment, the reference and sample beams come to the rapidly rotating chopper, which controls which beam enters the monochromator. In the open position, the sample beam is allowed to pass into the monochromator. In the closed position, the sample beam is blocked and the reference beam is reflected instead towards the monochromator. The rotating chopper means that the photomultiplier tube measures the light intensity alternately between the reference beam and the lower intensity sample beam. This double beam setup helps account for fluctuations in lamp intensity. Photons enter the monochromator through a small slit and then are reflected off a mirror onto the grating. The grating spatially separates the wavelengths. The dispersed light is reflected off the grating to a second mirror, which both reflects and focuses the light towards the photomultiplier tube. An exit slit right before the photomultiplier tube ensures only a very narrow range of wavelengths can enter the detector. In the photomultiplier tube, the photons strike a photocathode, causing electrons to be emitted. The electrons accelerate towards 9 consecutive dynodes, where a cascading effect of the electrons occurs to amplify the signal. The signal from the photomultiplier tube is converted into a voltage. The instrument separates the parts belonging to the sample and reference and takes the logarithm of the sample over reference signal. This is output as an absorbance reading. I hope this video has been useful for you. If you have any questions, please direct them to me or your TA. And thanks for watching.